Good afternoon, everybody. Thank you for logging in. And our topic this afternoon is the normal distribution. The questions have been made available for download, so hopefully you have the questions in front of you, but if you don't worry because they'll be up here on the screen as well. So let's start off by considering what a continuous random variable actually is, because some of us may not have studied continuous random variables before. We have studied discrete random variables, and in our last webinar we looked at a particular type of discrete variables. That was the binomial distribution or binomial variables. This afternoon we're looking at continuous random variables. Now, continuous random variables can take any value within a specified range. So an example might be the time that it takes a student to get to school. So you wouldn't say that it took the student exactly 3 minutes. Time is going to be a continuous random variable. So even if you think it took them 3 minutes, might be somewhere between 2.99999 minutes and 3.0001 minutes. So other continuous random variables might be something like height or your weight. Often continuous random variables are variables that can be measured. So there are some specific properties that we need to consider when we're looking at continuous random variables. Continuous probability distribution can be described by a continuous probability density function. Now, parts of this area of study have been removed from the 2020 study design, but we do need to understand the basics of a continuous probability distribution and the properties of a continuous probability density function, because the normal distribution is a type of continuous probability density function. So if we're considering a function that is a continuous probability density function, that function will be on or above the x-axis for all values of x, and the total area under the curve, so the integral from negative infinity to infinity, and we'll talk about those lower and upper limits, is going to be 1. So the total area under the curve is equal to 1. Okay, so those properties are really important. And to calculate probabilities using a probability density function, we actually use calculus. Now, maybe some of you never thought you'd be using calculus in probability questions, but that's exactly what we do. We find the area under the curve using calculus, and the area under the curve is equal to our probability. Now, I've done this intentionally. You might notice that we have the probability that x is between a and b, and one of those is inclusive and one is not inclusive. That was to remind me to say that with a continuous probability density function, because the area underneath any one point is equal to 0, the probability that x is actually equal to a or b is going to be 0. And so that means it doesn't actually matter whether a and b are included or not. And I will show you a better example of that in just a moment. This is the normal distribution. Well, it is a curve that is the normal distribution curve. It's a shape you may recognize as a bell curve. You might have heard that term before. If you have studied another math subject that looks at bell curves, you may have used approximations. We're going to do things a little bit more precisely today with calculus. So this bell curve here is going to be the curve of a normal distribution, but we need to first define our variable, and then we would write our variable, for example, if x is equal to, so if we said x was normally distributed and x is equal to the time it takes to get to school, for example, this notation is important to understand, similar to what we saw last time with the binomial distribution when we had to define x as a binomial random variable. This is saying x is distributed normally, and then we would write the mean. So we've seen that symbol mu before. And next to that, so comma, the variance. And you'll recall that the standard deviation is the square root of the variance. Okay, so that's the notation that we would use. Now, here is the function. Don't let that stress you out. Some of those symbols you would absolutely, and those numbers you would recognize, E, pi. We know that sigma is the standard deviation and mu is the mean, and we have sigma squared, which is the variance. Now, this formula is actually going to be given to you on your formula sheet this year. So that's the good news. You do not need to memorize that. It's not something that you need to memorize. But if you want to graph the normal distribution, then that is the formula that you would be graphing. So what I've done here is I have actually used a notes page to define the function down here, f of x. And I've just used SD for standard deviation. Please don't write SD on your test paper or your exam paper. Use sigma. And I have defined the mean, mu, and my function here is f of x. Now, I can change these values, but at the moment, the mean is 30 and the variance is 52. So if we were writing out x is distributed normally like this, we would write the mean, and then the second value is the variance. Just be careful with that. It's the variance, not the standard deviation. So if you want to know the standard deviation, you need to take the square root of the variance there. Okay, now because I have defined this function, I can quite easily sketch the graph. And this is, in fact, a graph of the normal distribution. Our particular distribution has a mean of 30, and it has a variance of 52. So I said at the beginning, to calculate probabilities using these distributions, we find the area under the graph. So we can be doing that on a graph page like this, or we can be doing it using an integral calculation. Okay, so before we do an actual question, let's have a think about how the mean and the standard deviation change the shape of the bell curve. Okay, the bell curve itself, you can see here, is symmetrical. So it doesn't matter how much I change the value of the standard deviation and the mean, it is going to stay symmetric. Okay, it's not going to be skewed in any way. One of the properties of the normal distribution is that it is in fact symmetrical. So this particular distribution here has a mean of 39 and a standard deviation of 6. Now, we learned that the standard deviation is a measure of spread. So standard deviation and variance are both measures of spread. And so if we increase the standard deviation here, which I'll do in a moment, what do we think might happen? Well, you would expect that the spread increases, but we recall that the total area under the bell curve has to stay as 1. The total area under the curve is equal to 1. And so when we increase the standard deviation, the spread does increase, but you can see that it's going to flatten out because the total area under the curve must stay as 1 unit. Okay, so likewise, if we decrease the standard deviation, then we would see our curve becoming polar. Okay, the total area under the curve is still 1. If we change the mean, maybe decrease the mean or increase the mean, hopefully from this little simulation here, you can sort of get the idea that this has something to do with translation. Okay, so, and if you have a good look at this function, we can see x minus the mean. So we can see that as we change the mean, we will be changing the horizontal translation. And now if we think back to the standard deviation, as we change that value, we are changing the dilation of the curve. Okay, so that is how the mean and the standard deviation changing will affect the shape of your bell curve. But they all have the same general shape, symmetrical. Okay, so let's jump into an example. Question 1. A random variable x is normally distributed with a mean of 70 and a variance of 18. Now, just be careful here. The variance is 18, so the standard deviation is the square root of 18. Find to 3 decimal places the probability that x is greater than or equal to 62 and less than or equal to 73. Sorry, strictly less than 73. Now, that brings me to what I was saying earlier about the signs not being so important here, which is quite different to if you think about discrete probability. We need to be very careful with our inequality signs and be really mindful as to whether we're including a lower value or not. So in this case, all of these 4 values will be the same, regardless of the signs, because we are going to look at the area underneath the bell curve between 62 and 73, regardless of whether the 62 is included or not in that calculation. Okay, so the probability for continuous random variables, the probability that x is equal to any one value is going to be 0, because the area under that particular value is 0, which makes sense. Okay, so what I've done here for us is I've already defined my mean and my variance. So I've calculated my standard deviation, square root of 18. And then I have defined my function. And this will allow me to actually look at the graph. So I've defined my function here. Now the question is asking us about the probability that x is between 62 and 73. And we can do this using calculus. And so we will find the area under the curve between 62 and 73. Now it should make sense as to why that curve must be above or on the x-axis for all values of x, because if any of the curve was beneath the x-axis, there'd be a chance that our integral was negative, and you can't have a negative probability, so obviously that wouldn't be possible. Okay, so I've calculated the integral here, and I get 0.731 if I'm asked for 3 decimal places, which is what we were asked for. Okay, and that's one way to do the calculation. Of course, we could do it on the graph itself. So we could go to menu, analyze graph, and then integral. And we can type in 62, press enter, and 73, press enter, and we get that same value. Okay, a few less decimal places in my graph settings, that's okay, 0.731. However, thankfully, someone very clever has predefined the normal distribution calculation in our handhelds for us. This is very exciting stuff. So I will get to a blank calculator page and show you where to do this. If you go to menu and then 5 and menu 552, okay, normal CDF, cumulative, obviously, and our lower bound for this question was 62. Our upper bound was 73. Our mean is going to be, with a mean of 70. And now that's asking for the standard deviation here. So just be careful. They're not asking for the variance. They're asking for the standard deviation. And there's the number that we were getting using the integral and also using the graph integral, 0.731. Okay, so that's how we calculate probabilities with the normal distribution. But a few more questions here we're going to go through. I might just add, if you do have any questions, you can type them into the chat, and there's teachers on standby to answer them as well. Okay, so question 2. The weight in kilograms of watermelons from a harvest at a watermelon farm are normally distributed with a mean of 10 kilograms and a standard deviation of 3 kilograms. If I was doing a test paper, I'd have a highlighter out. I'd be highlighting those key parameters. Find to 1 decimal place the percentage of watermelons in the harvest that weigh more than 12 kilograms. Okay, so what we really need to do is define our our variable. So they haven't told us a particular variable to use. I'm just choosing x. I'm going to say let x equal the weight of the watermelon, and then I will write down x is distributed normally. Remember, this is the mean and the variance that we write here. Okay, so the probability that our watermelon weighs more than 12 kilograms, we can work out, get rid of that, and we can work that out using our handy little function. However, as our upper bound, we are going to put infinity here, because if we're using a lower bound or an upper bound that is not given to us as a value, so they didn't say between, say, 10 and 12 kilograms, then we will use infinity for our upper bound or negative infinity for our lower bound. Now, why is that? Well, if you go back to the graph that we we're looking at, this function actually approaches the x-axis. It never touches the x-axis and it doesn't go beneath the x-axis. So that's why we need to use infinity as our upper bound. Now, we've found the probability that a watermelon is greater than 12 kilograms. The question actually asks us for the percentage. So we'd expect 25.2% of those watermelons to weigh more than 12 kilos. We can just multiply that by 100 there. Now, don't write that this handheld syntax. Don't write that on your paper, okay? You'd write this on your paper, you'd write the answer on your paper, then you'd multiply it by 100 and say 25.2%, but you wouldn't write the syntax on it. Okay, now, part 2 of this question is asking us to find the probability, this time not a percentage, but a probability that the watermelon weighs less than 7 kilograms, given that it weighs less than 10 kilograms. Okay, fantastic. So you don't need to define the function again at every part of the question. Just make sure that you've done it at the start of the question if the question itself hasn't done that for you. And this is conditional probability, okay? So we're being asked to find the probability that the watermelon weighs less than 7 kilograms, given that it weighs less than 10. Now, 10 happened to be the mean, I think, for this question, actually. So we are going to find this by finding the probability that our watermelon weighs less than 7, which is the intersection of the two, and dividing that by the probability that it weighs less than 10. And I've used a little sneaky trick here. I know that the probability that it weighs less than 10 is 0.5 because 10 is the mean. So half of the distribution is less than the mean and half will be greater than the mean. So you'll see here, just in case you don't believe me, if we put in the calculation there with lower bound of negative infinity and our upper bound of 10, then we can see that we get the same answer there. So the answer for part 2 of that question is 0.317. Okay, let's have a look at the third question. This question is describing a random variable x, normally distributed with a mean of 110, variance 16. So the standard deviation is going to be the square root of 16, not 4. And this time, we're actually told that the probability being less than, of x being less than a value a is 0.83, and we're asked to find, for one decimal place, the value of a. So you didn't think it was going to be that straightforward, hey? Just plugging numbers into a calculator. What I would do, and what I would tell my students to do in this case, is to draw this, okay? So definitely, if you get a question like this, I would do a little sketch. Now, you can actually see on there, I have just done this on the back of a scrap bit of paper. I've just done a little bell curve. It doesn't need to be perfect. I have labelled the mean 110. I've labelled my A value here. How did I know my A value must be more than 110? Well, the probability that A is less than, X is less than A is 0.83. So it's more than 0.5. So I've just plopped it here somewhere on the right-hand side. Now, I need to work out A. So how could I possibly do this? Well, one way to do this is with calculus. So I could define my function. I've done that already. I've defined my function f of x. I've changed my mean and my variance. And I know from looking at the picture that I've drawn that the area from negative infinity to some value a, so the integral from negative infinity to a of f of x is equal to 0.83. And I could actually set that up in my solve function, okay, to say that the integral from negative infinity to a of the function f of x is equal to 0.83, and I can ask my calculator to solve the function for a. Okay, now that is a handy way of doing it. It does, however, require you to have your function defined, which is a little bit time consuming, but hopefully that is making it very clear as to what we're actually doing here. We're solving an integral equation. Now, thankfully, somebody very clever who designs these calculators has actually pre-programmed into our calculator an inverse normal command. Now, I've already typed this in. I'll show you where to find it in a moment. Let's just double check. Our answer here was 100, A is 113.8167, and let's do that here. There we go. All right, so how do we do that? Well, we go menu and then to probability. So menu 5, 5, and before we were using menu 552, we're going to use menu 553, inverse normal. Now, this is asking us for the area, and the area that they want is the area to the left of your unknown value. Okay, it's always the area to the left of the unknown value, so or less than the unknown value. So 0.83 was our area, and our mean, we knew that was 110. And here again, be careful, this is the standard deviation they're asking for, not the variance. So we press OK, and there is our answer. Okay, so we do need to understand how to do it using the integral, but absolutely, if we were trying to do this quickly on an exam, we would use the inbuilt. Okay, so what about the second part of this question then? Given that the probability that x is greater than b is 0.92, find to one decimal place the value of b. Now, in this case, if we were to draw a little sketch of our bell curve, which here's one I prepared earlier, we can see that we need to be very careful interpreting what this is saying. This is saying the probability that x is greater than b is 0.92. So b has to be less than the mean, or quite a bit less than the mean. The area to the right, or the probability that x is greater than b is 0.92. The probability that x is less than b will be 1 minus this, so 0.08. Okay, and so we can do that using an integral equation. We can put in from b to infinity is 0.92 and find our b value. My latest just frozen a bit. There we go. Find our b value there. However, if we were using the inbuilt feature here in the calculator, you'll recall that we needed to type in the area to the left. So menu 553, this area will have to be, you can type in 1 minus 0.92 if you want to, or you can if you do that calculation much difficulty, then you can do that. And we'll type in the area to the left. Now we're getting the correct b value, but just be mindful when you're using inverse normal and it asks you for the area, it is going to be asking you for the area to the left of that unknown value. So we don't type in 0.92, we type in 0.08. And there we go, we found our b value. Okay, so question 4 is asking us to find a random variable, continuous random variable, I should say, w, with a normal distribution. The mean of w is 200 and the variance is 25. The values of a and b are such that the probability that w is between a and b is 0.8, where this is the middle 80% of values. Correct to 2 decimal places, find the values of a and b. I would say to my students, draw it. Okay, so let's go back here because I've drawn it somewhere. There we go. Here we go. I draw a little sketch. Now, the middle 80%. If you draw this, it becomes a lot easier to interpret. The middle 80% between A and B, that means we have 20% left, and this is symmetric, so it must be 0.1 area to the left of A and 0.1 area to the right of B. And so we can now, hopefully, work out what our A value is using our inverse normal calculation. Remember, to find an X value or a W value in this case, we will type in the area to the left, the mean, and the standard deviation. I'm just checking my, standard deviation is 5 because my variance was 25. Press enter, and I found that A is 193.59. I know that the area above, or from B to infinity is 0.1. So less than B would have to be 0.9. Okay, and so I can use my inverse normal calculation to work out my value of B. And you can even check that. You can then type them in down here and say, okay, well, using the normal distribution inbuilt function in the handheld, let's type in the values of A and B, the mean and the standard deviation, and we should get 80%, which is exactly what we get. We can also define, if you want to, you could define A here and define your B value here. It just might be a bit of a quicker way to check it rather than typing in the values again and then work out the calculation between A and B. It's just an alternate way to check your working out if you are using a notes page. Okay, so let's have a look at something called the standard normal distribution. So the standard normal distribution is useful, certainly useful to my parents because they didn't have fancy calculators that could work out the normal distribution calculations. And back in the good old days, your grandparents probably would have used the standard normal distribution, and they would have seen a table that looked something like this. This is just a snippet of the table. They would have been given the parameters for normal distribution and had to standardize their values and get Z-scores. Now, you'll look at this in more detail when you're studying it. Generally speaking, these are approximations. So the Z-score equal to 0 is equal to the mean. That's not an approximation. 1 standard deviation from the mean will be Z-score of 1, 2 standard deviations, Z-score of 2, etc. Now, what we are going to do is look at how to actually standardize some scores. So a nice little example down here, my sister and I, very competitive sisters, Hayley and Daisy, sat a maths test at different schools. Hayley's result was 94% and her class average was 80%, standard deviation was 6%. Daisy's result was 70%, her class average was 65% and standard deviation was 2. Now, if you and your sister get home and you're comparing your maths test results, obviously Hayley's score looks better than Daisy's. Let's standardize these and see who did better. Now, my score, a 94 with a mean of 80, standard deviation of 6. My Z score is going to be 7 on 3. Okay, so let's convert that, 2.33. So what does that mean? It means I'm more than 2 standard deviations above the mean. Okay, it's a pretty good score. No debating that. Daisy's result was only 70. Her class average was 65. And you can see these values changing as I change these. And her class standard deviation was 2%. Now look at this. Daisy's Z score is 2.5. So this means that Daisy was 2.5 standard deviations above the mean. She's actually done better, relatively speaking, than I did on my test, which is not surprising. She's very clever. So how is this useful? Well, we can use the standard normal distribution for questions such as question 5. If X is distributed normally with a mean of, well, we don't know the mean, U, and that is the variance, 5, and the probability that X is less than 120 is 0.9, find in 2 decimal places the mean of the normally distributed value X. Now we can draw this. Here we go. The problem is, if we draw it, we don't know the mean, so we can't use the inverse normal. We have the area actually, but there's no function that I can think of inbuilt that is going to tell us what the mean is. We can, however, if we know the Z-score, and if we know the standard deviation, and if we know the X-score, then we can find the mean. Now, something very important is that if we go back to our little graph of Z-scores, for a Z-score, the mean is 0 and the standard deviation is 1. Okay, the mean is 0 and the standard deviation is 1, which is what's written here. So if we get a look at this question, and I want to know what the Z-score is here. Can I work that out? Well, I can work that out if I know that for my Z-scores, the mean is 0 and the standard deviation is 1. I can work out using inverse normal that my z-score is 1.2815. I know my z-score now, here. I know my x value is 120, and I know my standard deviation that was given to me in the question. And so I can use the solve function here to solve the equation. This is the equation up here that we're solving, z equals x minus the mean of standard deviation. And I can solve that for the mean. Okay? So there's a lot more that we can do with the standard normal distribution. It's actually really interesting. We can look at symmetry properties. You can solve questions where you're asked to find the standard deviation or where you're asked to find the variance. We can also compare, as we sort of did before, results, etc. So there's another question on the sheet. I've sort of reached 5:30, so I might quickly whip through this just in a minute. The weight of packets is normally distributed with a mean of 450 grams. If the packet of biscuits is more than 10 grams underweight, it is considered faulty. And we found 3% of the packets are underweight. Now, what would I tell my students? I would tell them to sketch it. Okay, draw it. Here's our little graph. Now, I want to find the standard deviation. Any question like this where you're trying to find the standard deviation or the mean is likely to involve using z-scores. What I can do here is I can use my inverse normal with a mean of 0 and a standard deviation of 1 to find my z-score. You'd expect it to be negative because it's clearly to the left of the mean. If the z-score is 0, that's an x value equal to the mean. And now I can use my solve function. Okay. If I know that my z-score at that point is minus 1.88, I've got my x value, I've got my mean, and I'm solving for the standard deviation, I can use the solve function. Standard deviation is 5.319. I think it asked to the decimal places. So, yep, 2 decimal places, it would be 5.32. Okay, so that's a little introduction to the normal distribution and the standard normal distribution. I hope you've enjoyed this afternoon's webinar. Please stay on if you have any more questions. We're happy to answer them at the end. So thank you.